jump right in. In our last explainer, we had a lot of fun looking at the magic of Lambda expressions and how they radically clean up our Java code. But today, we're popping open the hood. We're going to explore the secret engine that actually makes those Lambdas run: functional interfaces.
We've all seen how Lambdas act like this amazing syntactic sugar. They completely remove all that clunky boilerplate code like anonymous inner classes. But they don't just exist in a vacuum. Underneath the surface, Lambdas rely entirely on the concept of functional interfaces. Honestly, without them, streams and Lambdas wouldn't even exist in modern Java. So what exactly is it? Well, it's remarkably simple. A functional interface is an interface that contains exactly one abstract method. That's it, just one. You'll often hear this called the single abstract method, or SAM rule, and it's a massive paradigm shift because this single method allows us to treat behavior as actual data. Because there's exactly one method to fulfill, we can pass a function around just like we would a regular variable or object. To picture this, imagine your code structure like perfectly matching puzzle pieces. If we set up a basic interface, let's just call it myInterface, and we give it a single abstract method called show, it perfectly fits that SAM rule. Since there's exactly one empty slot to fill, it is functionally pure. Now let's look at how this builds into the Lambda connection. If we declare an object of myInterface, we can assign a simple Lambda expression right to it, like one that just prints hello. And this works flawlessly. Why? Because the Java compiler looks at the Lambda, finds that one single show method, and just snaps them together. It knows exactly where that logic belongs. Okay, but here's a curveball. What happens if we try to sneak in another abstract method? Yeah, the whole thing completely breaks. If you have your valid interface with one abstract method, you've got the green light. But the second you add another abstract method, say display, it invalidates the whole setup. Your Lambda fails immediately because you've just introduced ambiguity. The compiler literally gets confused, wondering, wait, which method are you actually trying to implement here? And it throws a compile time error. Which brings us to a best practice you absolutely must adopt: the @functional interface annotation. You just pop this right above your interface declaration. Technically, yes, it's optional, but in reality, it's your compiler's strict safety net. If you or maybe another developer a year from now accidentally tries to add a second abstract method, this annotation guarantees the compiler will throw an error right then and there. It protects your code from breaking down the line. And seriously, don't just take my word for it. This is a hard and fast rule straight from the definitive guide, Effective Java. It explicitly says, always annotate your functional interfaces with the @functional interface annotation. It's just a crystal clear statement of intent. It tells anyone reading your code, hey, this interface was built specifically for Lambdas, preventing future maintainers from accidentally ruining it. Now, there's a really important nuance I need to clarify here. Notice how I keep saying single abstract method, right? I'm not saying single method. A functional interface can still have default methods, and it can still have static methods. Remember, Java 8 allows implementations inside interfaces using those default and static methods to help APIs evolve without breaking everything. So as long as there's only one abstract method, your functional interface is perfectly valid. So if you take away one key insight today, make it this: Lambdas depend entirely on functional interfaces because they provide that single, solitary target method to implement. It's the ultimate target typing mechanism. The Lambda brings the behavior, and the functional interface provides the exact type structure the strict Java compiler demands. And the Java creators knew you'd need this constantly. You might already be familiar with built-in ones like Runnable or Comparator, but there's a whole robust package designed specifically for things like streams. For instance, filter expects a predicate to evaluate a true or false condition. Map uses a function to transform elements, and for each relies on a consumer to act on an element without returning anything. The point is, don't reinvent the wheel. These built-in standard interfaces are there to do the heavy lifting for you. All right, I've got a quick micro challenge for you right now. Seriously, pause this explainer, open up your IDE or even just a notepad, and create your own simple functional interface. Don't forget the annotation, then write a quick Lambda expression that implements it. Doing this active learning exercise right now is going to permanently lock this concept into your brain. Go ahead, pause it, I'll wait. Okay, welcome back. Let's pull all of this together. A functional interface defines exactly one abstract method, which is the exact mechanism that enables those beautifully concise Lambda implementations. It's a brilliant illustration of the single responsibility principle. Your interface has exactly one reason to change, combining great design principles with super clean modern coding practices. So where do we go from here? Well, in our next explainer, we're going to take everything we've learned today and dive deep into the Streams API, where we'll see Lambdas processing data with mind-blowing efficiency. But for now, I'll leave you with this. Now that you finally possess the engine, are you ready to use it to process massive streams of real-world data? See you in the next one.